This is Nick, and today I'll be introducing the L2 presentation for Group 12. In the modern era, we are too reliant on renewable sources of energy such as coal, oil, and natural gases. In contrast, renewable sources provide a more sustainable energy source. These renewable energy sources are more sustainable, and in particular, our project focused on the generation of wind power. Wind turbines convert the kinetic energy from the wind into electricity through the rotation of the turbine.
The basic principle of a wind turbine is to extract power by transforming the kinetic energy of the wind into mechanical energy in the rotation of the turbine, and then through a generator into electrical energy. To achieve this, the turbine must rotate and generate as much lift as possible while keeping the drag low.
In order to extract the kinetic energy, the flow is slowed down by the blade, and to keep the rotation, we need to maximize the component of lift in the right direction, called the driving force. Hence, good wind turbines are designed with high lift-to-drag ratios. The effective wind direction is created by the true wind and centrifugal wind, as shown on the right by the red arrows. This is bent at the resultant angle delta, which is the summation of beta, the pitch angle, and alpha, the angle of incidence. It is important to note that our airfoil section was not chosen to be symmetric. Therefore, the lower surface has to face the incoming wind in order to produce lift in the correct direction. The rotational velocity is not constant around the blade, therefore the effective angle of attack varies. For it to be optimum at each point along the blade, the angle of pitch has to change, requiring a higher twist at the root because of the lower velocity and lower at the tip. The pitch angle was calculated through the formula shown, which is derived from trigonometry. An important design parameter is the tip speed ratio, also called TSR, the ratio between the tangential speed of the tip and the actual velocity of the wind. A low TSR triggers the inability to generate much power, whereas a high TSR generates a higher risk of structural failure, which could happen aligned to the plane of the blade due to centrifugal forces or perpendicular to it due to aerodynamic forces. The blade is most efficient when the circulation is roughly constant along the span. For high TSR, the chord length is inversely proportional to the radial distance from the hub, since the effective wind speed is increasing. To generate the accurate chord distribution, the best relation was used. The longer a blade is, the more energy it will be able to extract. Moreover, Cp is the ratio of power delivered to the turbine to the total power available in the area swept by the blade.
A separate blade and hub design was adopted for our wind turbine. In the preliminary design stage, simple circular jigsaw joints were conceived as they can be milled easily. However, the rotation of the blade about its jigsaw attachment renders this hub and blade design unfeasible. Next, non-symmetrical shapes were then tried for the jigsaw joints, from semicircular to complex shapes. However, complex shapes were unfeasible to manufacture, and another consideration were the centrifugal forces causing the blade to twist. Following that, the use of screws was introduced as a solution to counter the centrifugal forces from the blade rotation that might shear the blade out from the hub. Sufficient area for drilling was a secondary consideration. Employing the use of a shaft and hole in a circular blade joint addresses the problem with blade rotation, and a screw holds the blade from the centrifugal forces and also fixes the angle of attack of the blade. A hexagonal hub instead of a circular section was used to trim weight and to cater for accurate positioning of 3 blades and a nose cone. Semicircular pockets were also made in the hub to reduce weight. To join the blades, a double dovetail joint was implemented to improve locking and increase mating surface area for the epoxy. Following the assembly of our wind turbine, each blade is locked firmly to the hub by a bolt. This fixes the angle of attack. The design turbine requires individual removal and assembly of each blade onto the hub, which in turn allows the blades to be glued, finished, or even replaced individually.
SG6043 was chosen as the airfoil of the wind turbine due to its high CLCD as compared to other airfoils. In developing the blade, we first chose a tentative TSR to work with, a TSR of 4. Using the chosen TSR, we designed the wind turbine blade with a pitch angle and chord length according to Bett's theory. Q-blade was then used to simulate the performance. We then wanted to try to increase the power generated, the CP. We designed 3 more wind turbines at TSR of 4.2, 4.4, 4.6, and a comparison of the power generated, the CP is as follows. It can be seen that the CP for 4.2, 4.4 and 4.6 is much higher than the CP achieved for TSR of 4. To evaluate the structural integrity of the wind turbine blades, MATLAB was used to evaluate the aerodynamic loads and the bending on the blades as follows. It can be seen that in terms of stresses, a blade with a TSR of 4.2 has a suitable stress in both the root area and along the blades. Therefore, a TSR of 4.2 with a good balance of CP and stress distribution was chosen. NACA 4412 was chosen as the root of the turbine blade due to its larger cross-sectional area as compared to SG6043. This is done to increase the strength of the root. The final blade is as follows.
And that's the design aspect of our turbine.
The hub manufacture can be broadly categorized into 3 parts. The hub conceived initially was a cylindrical aluminum rod. The cylindrical hub was cut down to bring it to the size required. To prevent heating, a cooling agent was constantly sprayed while cutting was in progress. It was also ensured that the hub had a smooth surface. A CNC machine was used to cut the cylinder sides to make it into a symmetric hexagon, and drill holes so that the blades could be connected to the hub. Lastly, a keyhole was brushed so that the hub could be joined to the shaft during testing. Were 3D printed using ABS, which is a thermoplastic polymer. Each blade was printed in 2 parts and later glued together at the joint. The hubs and blades were sanded to give a smooth surface. The blades and hub were assembled using a countersink bolt.
The graph shows the power generated against the angular velocities for all tested wind speeds. The maximum power was generated when the wind speed was at 12 meters per second, which is approximately 33.6. Power coefficients and tip speed ratios are the maximum CP for each wind speed were shown in this table. The average TSR of the results was 4.248, which is pretty decent compared to our design TSR of 4.2. Maximum CP of 0.165 was obtained at wind speed 12 meters per second, and also the turbine self-started at 8 meters per second. In general, the data recorded gave smooth curves, and no anomalies such as effects of resonance and fluttering were observed. Here's our expectation and reality table, where there is fair agreement apart from the mass and the CP. We then came up for some sources of error. For the weight, we believe it is because of the limitations in the 3D printing machines. 3D printing is only consistent to a certain extent, which results in varying density within the blades and the cone. Also, sanding caused inhomogeneous removal of material from the blade. For the CP and TSR, wind tunnel effect exists in testing. However, Q-blade simulation doesn't include these errors. Therefore, in our design there were some errors. The broken wind tunnel has also caused induced drag.
In conclusion, the hub was considered as the part that needed most improvement. At first, the hub was designed from a very conservative standpoint, that is to ensure the wind turbine would spin and wouldn't fail. The hub design caused the turbine to be very heavy. By making the hub lighter, such as reducing the height of the hub and selecting a smaller diameter of the hub, we could have improved the power-weight function. Also, thinner roots could have been designed instead to make the hub lighter. After this testing, we suggest that we can reduce the amount of twists throughout the blade because the wind turbine stalled early at 1,600 RPM at 10 meters per second and 2,000 RPM at 12 meters per second. Moreover, the turbine self-started at 8 meters per second and recorded highest volts at 2,000 RPM at 12 meters per second, which is well below the 3,000 RPM limit. Although a relatively low merit function was obtained, the turbine manufactured was in line with the designed turbine. The tested results were reasonably similar to the calculated results, and the turbine has successfully performed under the required guidelines. This is the end of our presentation, and thank you very much for watching.